Good afternoon. We have the third and last propulsion presentation for the ME propulsion track students. And for this presentation, we have a liquid rocket engine, and it's by Mercury Propulsion. And with that, I will have the speakers introduce, or the speakers there over there, the panelists introduce themselves, and then I'll pass it over to William Carpenter, who's the design team lead.
Hello, my name is David Krantz. I'm an Embry-Riddle graduate with ME Propulsion. And in the industry, I work generally in modeling and sim, so I look forward to see what you have.
I'm Garrison Robertson. I graduated in May 2015 with an aerospace engineering degree, and I've worked on missile systems and FTE work since I graduated.
Daniel Danley, mechanical engineering faculty here, teaching thermal heat transfer.
Mike Fabian, mechanical engineering propulsion.
All right. Good afternoon, everybody. My name is William Carpenter, and I'm the design team lead for Mercury Propulsion. Joining me are Sirat Sanga, Tobias Fauser, Sean Thompson, and Pedro Pena. So this presentation today, we're going to start with a brief introduction overall to the project before going in detail into the current design of each of the individual subsystems of the project, before concluding the presentation, mentioning what we're going to do next semester in detail, and then opening the floor to questions. So overall, this semester the team was this year the team is tasked with designing, building, instrumenting, and testing a liquid rocket engine, which we've decided to name MP-1. Additionally, the engine will be designed in order to optionally accommodate an experimental ejector thrust augmentation system, which for the sake of brevity we will refer to as ETAS. So in order to do this, the team will need to design, build, and design and build a test stand capable of accommodating both MP-1 on its own and with ETAS installed. And we will need to be able to acquire thrust and other engine performance data in order to quantify and evaluate the thrust augmentation from ETAS. So a brief introduction to the concept of an ETAS. Essentially, it uses the high-velocity, low-pressure rocket engine exhaust plume in order to entrain outside air through an annular opening around the engine. And additionally, if this were installed in a flight vehicle, you would acquire additional entrainment through ram air from the vehicle's airspeed. Once entrained, that flow is mixed with the hot, high-velocity combustion gases leaving the engine, thereby acquiring additional kinetic and thermal energy, before finally being expanded within a secondary nozzle inside the ETAS in order to extract more thrust out of energy that the engine would have normally thrown away. So the ETAS, like I said, is experimental, and it's being designed by a student not on the team, but we are designing it in order to support that project should we need to. So we will not be discussing the ETAS itself in detail in this presentation, but it did drive some of the design decisions we made on the engine. So the overall project requirements is laid out in the original RFP, where to produce 200 pounds of thrust without the augmentation from the ETAS. The engine was to be pressure fed using some sort of inert gas pressurant to feed both liquid oxygen as an oxidizer and some sort of hydrocarbon fuel into the engine. Additionally, because this engine is not being designed for flight, it's purely a test stand article. It was to use a water cooling system in order to allow a runtime of at least 5 seconds. And additionally, during engine runs, the team will need to be able to collect thrust, pressure, temperature data from MP-1 and also various points within the ETAS. So some initial design decisions we made after initial research in order to start the project were to set a nominal combustion chamber pressure inside the engine of 300 psi. To help the ETAS entrain outside air, we set our nozzle exit pressure 2 psi below ambient, which for up here in Prescott equates to about 0.7 atmospheres. Additionally, we settled on a fuel comprised of a mixture of 70% ethanol and 30% water. This fuel mixture was used considerably in the early history of rocketry, and we like it because it's inexpensive and non-toxic. And additionally, ethanol allows for the easy mixing of water, which is an easy way to lower your combustion chamber temperature and overall make the engine easier to work with for test purposes. Additionally, we decided on gaseous nitrogen as our inert gas pressurant for the feed system. This is, for our purposes, it is heavier, but this is in a flight system. It's heavier, but for our purposes, much less expensive than the helium you would typically see used in industry. And additionally, we settled on a combustion combustion chamber contraction ratio, so that's the ratio of the cross-sectional area of the combustion chamber to the nozzle throat area of 10. That was based on research we conducted of similar sized engines and similar performance engines to MP-1. So moving into just a brief overview of the preliminary overall design of the engine. You can see a fully assembled view on the left and an exploded view on the right. It starting from top to bottom. There's a fuel manifold that distributes the ethanol to where it needs to be on the forward side of the injector plate, after which it's injected into the engine, which is formed from a single piece combustion chamber and nozzle surrounded by a cooling jacket through which the water will flow. And then the cooling jacket is held in place with a nozzle flange that bolts onto the nozzle into the combustion chamber. And now I'll hand it off to Sirit Saini to talk in detail about the combustion chamber and nozzle design.
Thank you, William. For this section, I'll be going over two components of the engine, starting with the combustion chamber and nozzle, following with the water cooling jacket. Starting with the combustion chamber and nozzle, here on known as the engine. As William mentioned, the requirements have that the engine must withstand a pressure of 300 psi. It must have a nozzle exit pressure below ambient pressure. It must be water cooled via a cooling jacket, and it must be manufacturable in the Aerospace Experimentation and Fabrication Lab here on campus, here in Colby XFAB. Starting with the design decisions, reiterating a few key facts that William mentioned. Our fuel composition will be 70% ethanol with 30% water. The engine itself, highlighted in yellow in the picture on to your right, will be a single machined piece, meaning the combustion chamber, the converging nozzle, and diverging nozzle will be all one entity. There will be no welding in this engine. And finally, as W mentioned, the nozzle exit pressure will be 2 psi below to help support the ETAS should it be an option on our engine. So starting off with the initial design parameters that we mentioned earlier, we inputted those decisions into rocket propulsion analysis. It's a software program where the user may put in desired inputs, and the program will give you the respective outputs to meet those requirements. Our PA gave us an overall chamber dimension of 2.44 inches for the diameter, and the overall chamber length will be 4.46 inches. Our PA also gave us our nozzle dimensions. We'll be expecting a nozzle throat diameter of 0.78 inches, a nozzle exit diameter of 1.77 inches, and an overall engine length of 6.34 inches. After getting the parameters for our engine, the material selection was next. So we made a material criteria. We started with 300 series stainless steel. We chose stainless steel primarily due to its mechanical properties, focusing on the yield strength to make sure that the engine will withstand the pressures that we want and the temperatures that we are expecting. And then also the thermodynamic properties, focusing on the thermal conductivity in order to perform a thermal analysis for the expected heat energy coming from the engine, going through the wall and through the water cooling jacket, which I will touch on here in a couple slides. Out of the 3 analyses we'll be performing on the engine, 1 is completed, and we are currently in the second analysis. The first analysis is the hoop stress analysis, and we did the 4 stations through the engine. The 4 stations are the inlet, the chamber, the nozzle throat, and the nozzle exit, respectively. Starting off with the equation of sigma is equal to the expected internal pressure multiplied by the radius at that location divided by the overall thickness at that respective location. In order to calculate the expected hoop stress, we used varying thicknesses in order to help determine the overall thickness for our engine. We started with stainless steel 303 as a base choice. The yield strength of stainless 303 is 415 megapascals, but considering an industry safety factor of safety of 1.5, the overall yield strength is 277 megapascals. As you can see in the table above, highlighted in yellow, that is the highest expected hoop stress we'll be seeing in our engine, which is about 6.4 megapascals. Therefore, the consensus is that the expected hoop stress is far greater than the overall yield strength of our material. Therefore, pressure does not play a key role in determining the overall chamber thickness, or engine thickness in this case. Starting into the second analysis, we performed a heat transfer analysis in the engine. We looked at the critical location of the nozzle throat, because that is the hottest element of the overall engine during operation. Assuming a steady state operation, the Q prime G, which represents the expected heat transfer from the gas, will be equal to the amount of energy going through the wall, which will then be absorbed by the coolant, in this case water. We started on the chamber side. As you can see the equation there, Q prime G is equal to the heat transfer coefficient of the gas multiplied by the area, which is the circumferential area of the nozzle throat, multiplied by the temperature difference. From RPA, we are able to determine the following as highlighted in red in the equation above. As a result, we can set a desired wall temperature of 840 Kelvin, which is also determined by our water cooling jacket capabilities, which I will touch on in a future slide. So as a result, we can solve for the expected maximum heat energy at the nozzle throat at a given point. This is not represented throughout the entire engine, but in that one moment. As you can see, we're expecting in that area, respective area of the nozzle throat, about 2.79 megawatts per meter. It's a very large number, and it can be attributed to both the heat transfer coefficient of 20,751 watts per meter squared Kelvin, as well as the very large temperature change between 3,000 Kelvin and 840 Kelvin. The 3,000 Kelvin was determined from RPA. That is the hottest point that the engine will be experiencing, but it will not be carrying throughout the engine. So, as I mentioned before, I'm in the middle of the thermal analysis for the engine because that was just at one given point. Through iteration, we can solve for the overall total expected heat energy to be coming from the engine, as seen in the equation above. So carrying on into detailed design, we will be performing this iteration, not only for 303, but of all steel types of interest, such as 304, 309, and 310. And once we receive our analysis, we will determine we will finalize a wall chamber thickness that meets both our pressure and temperature requirements. And once the thickness is solidified, we'll be able to present our final designs to the machinist and AXFAB for fabrication beginning in hopefully January of 2017. Starting into the second component now, the water cooling jacket. As mentioned earlier, the cooling jacket must be able to absorb the heat energy that is expected from the engine. It must be self-sustaining with the initial start from the operator, and it must be able to run through the entire duration of the test, meaning it is the first component to turn on and it will be the last component to be turned off. Some of the design choices for our cooling jacket is the cooling jacket will be a straight pipe that will be enclosing the engine. As you see in the picture there highlighted in light blue, that is the area in which the water will be flowing through. We will have 3 entry ports at the nozzle exit and 3 exit ports at the top of the chamber. The entry ports are located at the nozzle primarily because the nozzle will be the hottest element on our engine, therefore it is the first element needed to cool down. The sleeve will be secured between the base of the chamber and the nozzle flange. As you can see highlighted in red there, the top 2 red squares represent essentially an indented circumference where the sleeve will slip into, rest against the base chamber, and then the 2 bottom squares represent the bolts that will go from the nozzle flange into the nozzle exit, therefore pretty much securing the sleeve in between the 2 ports. We are not planning to remove the water cooling jacket once it is installed. We'll be predicting the amount of heat transfer the cooling jacket will be able to absorb. Right now, we will be using a 500 gallon per hour pump to cycle the water from an ice bath. This gives an estimated flow rate of 1.1 pounds mass per second. And that is an image of our current cooling jacket sleeve, as I mentioned earlier, that will fit between the base chamber and the nozzle flange. Carrying on into detailed design, we will calculate the energy absorption capability of water, meaning how much energy our coolant can absorb from the engine. Then we will be performing a structural test to make sure that the cooling jacket will be secure. And then we'll be purchasing our water pump in January and then be beginning our water flow testing. I would like to pass it back to William now, who will be discussing the feed system.
Thank you, Sierra. So the requirements for our feed system, as driven by both the RFP and the overall design for the engine, was, again, we're using gaseous nitrogen as the pressurant for the system. And additionally, based on hardware available, left over from previous university projects, that we're setting our maximum allowable feed system pressure at 450 psi, which works with the hardware we have and also provides us plenty of margin for loss going through the feed system leading up to the engine. Additionally, because we are working with liquid oxygen, at least the LOX half of our feed system will need to be LOX compatible, which is to say that it's made out of materials which will not react with LOX while in contact with it. With that in mind, we're going to utilize copper and stainless steel components throughout the LOX side of the feed system. And additionally, we will be selecting all valves for that side of the system to be oxygen safe, which is to say the metals they're made of, as well as any lubricants or packing materials used in the valves, are not going to react with the liquid oxygen. And then it was also to be cryocompatible and able to function at the cryogenic temperatures of liquid oxygen. And additionally, we've selected 4 valves within the system, which I'll point out in future slides, for electronic control. Specifically, we're going to use solenoid actuation of both the fuel and LOX main valve, as well as a small chill valve on the oxidizer line. And then we will have a motor control of the throttle valve on the fuel line. So this diagram is a general overview of the feed system, without wasting too much time going into detail, but you can see the black lines representing our gaseous nitrogen pressurant feeding into the green liquid oxygen half of the system and the red ethanol half of the system, pressurizing those 2 tanks and pushing the fuel through to the engine. So call that now the valves I mentioned on the previous slide. So in the box on the right, from top to bottom, are the main fuel valve, the main LOX valve, and the injector chill valve. Those are the 3 valves which we will be actuating via solenoids. The 2 main valves are the valves through which the propellant flows when you're running the engine. And then the injector chill valve on the LOX side is a valve designed to let a small amount of liquid oxygen flow through the system in order to chill the last little bit of plumbing, as well as the oxygen injector to ensure that when we go to run the engine, we will actually be injecting liquid oxygen rather than oxygen that's boiled off into a gas. And then the valve in a box on its own on the left there is the fuel throttle valve. That's a needle valve which will be turned via a motor, and that will run off of the control system, which Tobias will discuss later. It will take chamber pressure data from the engine and use that to back calculate our expected flow rates getting of each propellant, and then the system will turn that knob to adjust our mixture ratio in the engine. Moving on into the injector, which is where the feed system interfaces with the engine. So the requirements of the injector was to operate at a target injector pressure drop. So that's the difference in pressure between immediately inside the injector and the combustion chamber pressure of the engine. We're setting that at 60 psi, based on an industry rule of thumb for pressure-fed liquid rocket engines. That pressure drop should be approximately 20% of your combustion chamber pressure. And additionally, through RPA output, we're targeting an oxidizer flow rate of 0.49 pounds per second and a fuel flow rate of 0.38 pounds per second. And additionally, to ensure good combustion of the propellants, the injector will need to atomize and mix the propellants after injection. In order to accomplish this, the team's decided on using a like-on-unlike doublet injector arrangement. So that's essentially a stream of fuel and a stream of oxidizer exiting at an angle and impacting one another, which does meet our requirement of directly mixing and atomizing the propellants. We also chose this because it has been manufactured on campus before by similar groups, so we know it's something we can make. And it's been widely used in industry over decades, and there's a lot of data available for this type of injector. So we know it can be used in stable operation over engines using various propellant combinations over a wide range of scales. And additionally, our research has found this injector type successfully used on engines similarly sized to MP-1. We did evaluate 2 other possible injector types. First is the like-on-like doublet, which is similar to the like-on-unlike, except as the name would suggest, it's 2 streams of the same fluid impacting one another, which does atomize the propellant, but it does not adequately mix the propellant for our needs with MP-1. And then we also evaluated an oxidizer fuel oxidizer triplet, which is 2 angled impinging oxidizer streams with a single fuel stream coming up the middle. However, industrial experience has shown that that injector type is very sensitive to combustion instability issues, and additionally would provide greater manufacturing challenges for us because each injector element would have one more very precisely placed hole that would need to be drilled. So moving on with the like-on-unlike injector port, after choosing the geometry, we have to size our injector ports using the equation on the right, which gives you your injector port area as a function of the total mass you want to flow through, unitless discharge coefficient representing the loss you get through your injector port, as well as the density of the propellant and your total injector pressure drop. So based on research of similar injectors, we assumed a discharge coefficient of 0.75, and that, given our design point of 60 psi and our desire to use 4 elements in total, resulted in an area for each oxidizer port of 0.0037 square inches, which, converting that to the closest standard drill bit size, is a number 50 at 0.0038 square inches. And for the fuel, we're looking for a target area of 0.0034 square inches, which again, putting that into a standard drill bit size, results in a number 51 drill bit of 0.0035 square inches. Next is the total impingement angle, so that's the angle formed between the 2 jets of propellant. Industry rule of thumb sets that at 60 degrees because that's been shown to provide a good balance between making sure that your propellant stream isn't very long from leaving the injector face before impingement, but also not providing very much splashback of propellant onto the injector plate, which would create an unwanted amount of heat transfer into the injector. So after choosing that, you have to decide your fuel and oxidizer, each of those individual impingement angles. So your desired outcome is to have a resultant angle of the momentum of those two impinged streams, or referred to as delta, of 0 degrees, meaning it's shooting straight down the chamber. We found through trial and error that if we set both of them to 30 degrees, we get a delta of 1.44 degrees, slightly towards the center of the chamber, which, if we're going to be off in either direction, that's more desirable because it's ensuring that after impact, your two propellants are going to be collecting in the center of the chamber rather than going out and hitting the wall and transferring lots of heat into your combustion chamber wall. And then the final step is deciding the impingement distance, so the linear distance between the face of the injector and the point where the two streams impinge. That's set from another industry rule of thumb that you would like the ratio of the length of your propellant stream to the area of the port it comes out of to be approximately 5. So setting that with our oxidizer stream resulted in a desired impingement distance of 0.3 inches. So all those fed into the final injector design, which you can see on the right side, the face that actually faces into the engine. Those are our 4 injector elements arranged in a plus shape. In the cross section, you can see the 2 oxidizer streams coming out of the center and the 2 fuel streams coming in on either side of that, impinging on one another. And on the back of the injector, or the front, excuse me, of the injector, you can see the cooling passages where the fuel is fed into the small circular depressions on the outside and is run back and forth across the injector face to provide some amount of cooling before finally being injected. And we are currently working on performing thermal analyses to ensure that the design we have there will provide adequate cooling of the injector face. So moving into detail design next semester, our tasks will be to complete that thermal analysis to ensure the design we have will work and possibly update it to ensure we get adequate cooling of the injector face. And then after that, we'll be able to order materials and begin fabrication of both the injector and the fuel manifold. And then the next step would be to perform water flow testing to determine our true values for a discharge coefficient and also the true pressure drop we get in our propellant manifolds. And now I'm going to hand it off to Tobias Bowser to talk about the control system.
So for the instrumentation and the control system that's involved there, we came up with this basic block diagram just to give you a overview of how everything is going to be interfaced to the engine and the feed system itself. So on the left, we have the sensors and valves, and then those signals will be going into any application that's necessary for the before they get to the real-time system, where they will be interpreted and converted for the ground station. I'll be focusing on the sensors and valves as well as the amplification for the most part. And so in order to meet the requirements of our system, we'll be looking at temperatures of 90 Kelvin for the lock side, all the way up to 840 Kelvin, which was the inside of the chamber wall. But since our sensors will be on the outside of the chamber wall, we actually won't experience that high of a temperature. For the chamber pressure, we're looking at 300 PSI as is our design point. And for the engine thrust, we're looking at 200 pounds force without ETAS, and then up to a minimum of 210 pounds force with ETAS, which was a design point of 5%. For, just to give you a quick overview of our real-time system, which drove some of our decisions for the sensors themselves, we have supply voltages of 3.3 volts and 5 volts, and as well as 16 analog inputs, which will be able to be used for all of our transducers. For the analog inputs, they allow the range of 0 to 3.3 volts for our transducers. In order to collect the temperatures that we are looking at, we went with thermocouples instead of resistive type temperature sensors because they're more robust to vibrations. And in order to get the temperature ranges that we're looking at, we're using type T and type K thermocouples. The type T will cover the LOX temperatures up to ambient, and then we'll use the type K for ambient and above. For the signal characteristics of the thermocouples, they're a differential signal that are in the millivolt range, and for the temperatures that we're looking at, it's going to be negative 5.3 millivolts up to 23.5 millivolts. For the amplification of the thermocouple, we already have the circuitry designed and fabricated. We're using the 808495 amplifier, which is an instrumentation amplifier specifically made for type K thermocouples, but also works for type T. And for that, it has a 122.4 gain, which gives us negative 0.65 volts up to 2.88 volts on the output. It has a voltage reference in order to shift that negative voltage up so that we can get it to our ranges that we expect that we're using for our data acquisition system. For just an example, for the 90 degrees Kelvin, that will have a negative voltage. We can use a 1 volt V reference to push that up to 0.35 volts, so then it'll be an acceptable range for our system. For the chamber pressure collection, we've already chosen Honeywell PX2 series because of its lower price point over the other choices and with similar pressure ratings and outputs. So that's rated up to 500 psi. So if we decide to use it for our tanks, we can do that, and it will also work for our 300 psi in the chamber. The significant characteristics are that it needs a 3.3 volt supply, which our system has, as well as the outputs 0.33 volts up to 2.97 volts. For the engine thrust collection, we've chosen a Type S load cell, the Fidget 3138, which came in at $45. It's pretty cheap compared to, it's not cheap, it's inexpensive compared to the other options. It's rated at, nominally rated at 220 pounds force, but can safely operate up to 265 pounds force. For the single characteristics of the load cell, it needs excitation in order to give an output, and it's also a differential signal like the thermocouples. For the fuel throttle valve selection, we came up with a 40 psi pressure drop design point across the control valve, which came from basically our 450 psi maximum at the tanks, which allows 50 psi through the feed system, 40 psi across the control valve, and then the 60 psi across the injector plate, which gets us at 300 psi into our chamber. For that 40 psi, it corresponds to 0.4 for the control valve CV, which is how we chose this particular valve. It has a max CV of 0.76, which gives us a good working range for the 0.4. And so far with the work completed with the sensors, we've actually prototyped our thermocouple amplification circuit boards, and we've spot welded some type K thermocouples. We were actually able to measure reliably about 0 degrees Celsius in the ice bath without any calibration, so it's looking good so far. And then for future work with the, for the real-time system, we've actually been able to collect data with that as well so far. Going into detailed design, we are focusing on sensor calibration and testing with all of our sensor types, as well as doing a full integration with all sensor types into the real-time system. Now I'd like to pass it off to Sean Thompson to go into more detail about the hardware and software of the control system.
Thanks, Tobias. For this part of the presentation, I'll focus on mostly the hardware and software of the control system itself. So this is, as you've seen, the instrumentation and control overview. I'll focus mainly on the real-time system, the ground station, and the valve control and how they play into controlling and monitoring MP-1. So our initial control requirements are as such. We have to autonomously control the engine during runtime or during testing, and we also have to simultaneously collect engine data for post-burn analysis. To do this, we developed a real-time system that closely monitors and controls the system while simultaneously sending the data to a graphical user interface that an operator at our ground station will be able to look at to visualize all the pressures, temperatures, and thrust that the engine is currently producing. So for our real-time system, it consists of a single development board, which is the Explorer 16 by Microchip. We chose this development board because it offers different processor options as it's swappable out of the development board to give you either higher performance, lower power, anything that you could need. So we're sitting right in the middle with the PIC24 FJ series, which offers up to 16 MIPS or 16 million instructions per second, which is very decent for what we're trying to do with it. It also offers an onboard analog to digital converter with 16 channels and 10-bit resolution with a sample rate of 500,000 samples per second. What this means is that if necessary, we can take a sample every 2 microseconds and feed it into our system to produce an output. So the software running on our Explorer 16 is a real-time operating system that we designed that basically combines the control system and the data acquisition system into one easy software port. This was developed from free open source software, so we spared no expense during development, and it offers the ability to schedule software tasks so that they have deadlines, and the system is built to meet those deadlines. So when we're running at a 50 hertz rate, when calculating all of our inputs from pressure and temperature and calculating what servo angle we're able to do, currently we're able to work at 50 decisions per second precisely monitor what's going on in the system. Additionally, the real-time operating system came with tracing and profiling software that shows you where you are currently at when the software is running, and after a test shows you where you have been, which is very useful for debugging, and again, offered no cost for us. So the real-time system is capable of two different kinds of outputs. Its first output is for the graphical user interface. The real-time system is capable of offering 70 ASCII character messages that are then sent to the ground station and parsed. Currently, they are set into two different sections, which you have your tick count and your message buffer. The tick count is roughly the elapsed time in milliseconds that the test has started and gives you kind of an overview of when certain things have happened, whereas the message buffer will most commonly be either an error message or something that the operator needs to look at, but it's most commonly the analog to digital converter values of all 16 channels in succession. We were able to compress the data by switching from a base 10 system to a base 16 system known as hexadecimal, just to give us a little bit more margin in our 120 kilobit per second transmission speed. The other output that we are capable of is the valve control. And so the real-time system has to take care of the startup and shutdown procedures for the liquid rocket engine, which it does by opening and closing solenoid valves at very precise times before and after starting and shutting down the engine. Additionally, during runtime, it is capable of controlling the mass flow rate of the ethanol flowing through the system. We do this with a pulse modulated signal that is sent to a servo that shows what the exact angle of the servo is. Once again, that decision happens 50 times per second, and due to the nature of the design, we're able to create this open loop control because we know precisely what angle our servo's at based on the signal that we're providing it, and we know whether or not the solenoid valve is open or closed based on whether or not we're providing it an input. For our ground station graphical user interface, we started off with three main objectives. It had to allow an operator to visualize the temperatures, pressures, and forces of the system in real time. It had to act as external data storage for redundancy with onboard data storage, and it was supposed to provide the post-burn engine analysis so that after the post-burn we can see beautiful graphs of everything that happened in the system. This is a mock-up of the current graphical user interface. As I said before, analog to digital converter had 16 channels, so therefore the GUI then supports all 16 channels. As you're setting up the GUI, you're able to set every single channel to a pressure, a temperature, or a load cell, and then you're also able to calibrate those channels so that they have nominal operating points. So you're able to set sensor data coming in to be at a nominal point, at a warning point, or at a critical point, which would most likely need operator input. This is so that when you are viewing it as the operator, you can look down and see they're color-coded so that you can see, okay, everything's green, everything's nominal, we don't need to worry about it. When things start turning yellow, you need to start making sure that either someone is capable of shutting off the system or that everything's operating correctly. And down at the bottom is the raw serial data that is coming from the real-time system and is also logged simultaneously onto the computer that will be acting as our ground station. Moving into tasks for detail design, we are working to finalize the mathematical model of our control system. This essentially takes all of our inputs that we provide into the system and provides the output that our real-time system then correlates to the next input of our system. We're working up just to make sure that everything is designed appropriately so that when we give it an input, we know the exact correlated output that the real-time system will have to measure. Next, we need to design the algorithm for storing and offloading data from the onboard memory that I did not talk about in this presentation, I just now realized. We have onboard data that is used in redundancy with the the data on the ground station, so that if something were to happen to either the ground station or the real-time system, we have two different locations for that data to be stored. And finally, the ground station user interface will need to have the post-burn analysis functionality implemented so that once we're done with the test, click one button, all the data is loaded into these beautiful graphs and we can see everything that happened in the system. Now I'd like to turn the presentation over to Pedro Benny to talk about the test apparatus.
Thank you, Sean. So we were able to derive satisfied 2 requirements from the RFP in order to implement our test stand. The first of which was to integrate with pre-existing infrastructure. Embry-Riddle does own a test site behind the RC field on campus, and we would like to reinvent as few wheels as possible and use as much hardware and infrastructure that the university already has. Our second requirement will also accommodate the MP-1, the ETAS, and instrumentation for both systems, so all critical instrumentation would be on board the test stand during testing. So above, you'll see a test site example. This specific example is from Strava Designs from last year. They were also working on a similar liquid rocket engine. Since we are also building liquid rocket engine, our test site will be laid out very similar to them. In the test bunker is specifically where our personnel will be during testing. The test bunker is meant to protect our students during testing. The test cell is where our test stand will be located and is where our rocket engine will be tested specifically. It also adds protection for the area because it is a 3-walled area made out of 6-inch thick concrete with an open area downrange as well as an open top. This is going to be a side view of our test stand. We will be working on specifically the test stand that's going to be placed inside the test cell. So the rail system and the test platform, the MP-1, the ETAS, and the instrumentation, which includes the load cell and the valves, etc., will be mounted directly to the test stand. So in order to simplify mounting of our rocket engine onto our test stand, we decided to enclose our rocket engine. And this goes back to the optional ETAS objective that we had earlier that William touched on. We will be covering our rocket engine in a pipe similar to the ETAS, which will allow us to manufacture just one mounting scheme in order to attach both our ETAS and our rocket engine onto our test stand. So it simplifies, it minimizes machining, manufacturing time for Mercury Propulsion. It also takes safety into consideration. If for some reason the rocket engine were to fail, it would add an extra layer of security for any debris that were exiting the test stand. So another set of decisions for the test stand, we decided to fire horizontally, and this goes back to our initial requirement to integrate with the hardware and infrastructure that we have on campus. This simplifies our system. We won't have to design or implement a vertical testing design. We can just bolt on directly into the test cell. We also decided to implement a rail system, and this is to accommodate our load cell. It will provide translation for our load cell in order to measure thrust, as well as it will secure our rocket engine down to the test stand. We've also decided to use a testing platform provided by the College of Engineering. And because it hasn't been implemented before in the test cell, we are actually capable of installing this test platform flush with the back of the test cell in order to minimize any space between instrumentation and the rocket engine. So for the rail system, we decided to actually buy our carriage and rail system from McMasterCar.com. And we chose that's part 6273K13 from McMasterCar. This carriage will actually be capable of bolting on directly to the cover that will be covering our rocket engine. It's got 4 M4 screw holes, which will attach to the bottom part of our covering. This carriage also is capable of carrying about 225 pounds, and with an expected expected weight of a rocket engine of 15 pounds is much better than will be needed. The corresponding rail system that will go over this carriage fits directly. It comes with the carriage. When we did a preliminary material analysis on this carriage from McMasterCar, it is capable of securing our rocket down to 300 pounds. And that is if we were to pull our rocket engine perpendicular to the slide. So this would be in the case of a failure if the rocket engine decided to try to pull up, it would not be capable of doing so. Our rail system would be able to secure our rocket engine. So on top of that, this rail system has been used commercially. We know that it's low friction, so it would interfere very little with our instrumentation and our load our thrust and data collection, as well as it's very inexpensive. We can buy 2 carriages, which we expect, and 1 rail 25 centimeters long which we could actually customize in the machine shop here on campus. We can cut it, split it up into 2 sections. Excuse me. And this is in order to be able to accommodate the ETAS, because the ETAS is expected to be much longer than the original rocket engine. So we could possibly have a modular system where we could attach the ETAS on 2 separate carriages and 2 separate rows. On top of us, up ahead, you'll see the test stand configuration. We've decided to mount our rocket engine directly to the test stand, like I mentioned earlier, using a rail system. Our valves, our main fuel LOX valves and our chill valve will be hard mounted directly to the test stand. And this is to allow for electronic actuation of those valves remotely. We will also attach our fuel throttle valve to the very back of the test cell. There is a shelf on that test cell on which we can set that throttle valve. And all the propellant tanks and the rest of the plumbing will be placed outside of the test cell. And this is for safety considerations. If for some reason the MP-1 were to fail, we would not like to compromise the propellant tanks. Additionally, College of Engineering plans to implement safety upgrades, which are yet to be determined at this time. And Mercury Propulsion plans to be flexible with this test stand configuration in order to be able to integrate with that system, should it be removed. So moving into detailed design, once all of the subsystems have been finalized and all instrumentation has been selected, we can model that in CATIA and actually make sure that all of these subsystems fit together and integrate with the test cell and test stand. And then we will move forward with fabricating the test stand and actually installing it out in the test cell. And with that, I will hand it over to William for labor hours.
Thank you, Pedro. So the team labor hours for the semester, we have our predicted labor hours shown with the gray line and our actual completed hours shown with the red line. As you can see, at this point in time, we do have a deficit of approximately 111 hours. However, the predicted hours are more of a guideline set out at the beginning of the course to help teams stay on track. And also, additionally, they are set up assuming that a team is starting completely from square one at the beginning of the semester, whereas Mercury Propulsion did benefit from some work that team members had done over the summer leading into the project. For the current budget of the project, the team currently has $2,000 available to it, $1,000 from College of Engineering and an additional $1,000 from the Undergraduate Research Institute. So as you can see, totaling up the estimated budget currently of each individual subsystem, we are slightly over that $2,000. However, those estimated budgets are created based on deliberately highball estimates of the costs of materials. And we do expect that to continue to fall as the team finalizes more design decisions and does more research and finds less costly ways to accomplish the project. So overall, at the end of detail semester, we do expect to be able to remain within our budget. Finally, moving into conclusions. So again, brief overview of MP-1. Engine designed to produce 200 pounds of thrust, burning liquid oxygen and ethanol, utilizing a pressure-fed propellant system. The mixture during engine runs will be controlled by a real-time operating system, and it's designed to possibly mate with a experimental ejector thrust augmentation system. And then full project moving forward in detail design, starting in January, we'll be finalizing our combustion chamber material design before purchasing raw materials and beginning machining and manufacturing of the engine, and as well as purchasing any stock off-the-shelf components used in the test stand and feed system, as well as the instrumentation and control system. Continuing after that, we'll begin the test program for the engine, which starts with water flow testing of the injector, again to experimentally determine certain properties of the injector and fuel manifolds. Finally, we'll be pressurizing the feed system and conducting valve actuation tests before conducting independent cold flow tests of each half of the feed system before finally leading into the ultimate goal of this project, which is a hot fire test of MP-1. So thank you for listening, and I'd like to open the floor to any questions.
Okay, cool. Yeah, overall, a great job. I'm really interested in learning about what you guys are going to do, and I'm looking forward to seeing you guys in the spring when it's all together. First question is, how are you going to actually manufacture the engine itself? Because if you're making it out of one solid piece, how do you do that?
Right. We have been talking to the machinists here on campus in order to manufacture that. Right now, everything we've heard indicates that through a combination of both lathe work and a CNC machine and AXTAB, we should be able to manufacture that here. But of course, the design is very much being fed by their input, and we'll work with them to make sure that we can do that.
Okay, yeah, because that's going to be an expensive, if you were in the real world, that'd be very expensive.
Right.
So, and then I don't really have too much else, but I thought it was a really good job. You linked really well forward and back. Quite often you mention other people's sections, or you would say later on we'll talk about this. So it helped you kind of keep track of when things were going to happen. So I wasn't left curious if you're going to actually talk about it. You know, just things like that. That was good. And then also on slide 31, starting there, I thought it was a really good job how you showed your process of how you determine what you're going to use. Like that's really important for your just presentations like this. It proves your logic instead of just saying we chose this. This is why we chose this. So I thought that was squared away. And then, for example, on like 51 again, where you showed the control overview, you had mentioned that I'm going to be talking about this specific section of this, so you can see what you're going to be talking about plugs exactly into it. So I really didn't have too much, but I thought it was overall a really good presentation for sure.
Thank you.
All right, I'd like to iterate, that was a very well presented project. It was very clean and you told the story very well. It's also a very well thought out project. I don't think I have too many really major things. I do want to touch a little bit on that single machine piece there. That's also your most likely point of failure. What would be the cost and time schedule to replace that if you needed to?
So just with the nature of both the budgetary and time constraints of the project, we unfortunately, if we do experience an engine failure, that is essentially game over for the project. We do not have the time or money to actually machine another engine, but that was always going to be the case unless we were somehow able to acquire significantly more time or significantly more money for the project.
Okay, so that's something to really keep an eye on. Another thing, just one idea that I want to make sure is swimming around in your heads with the cooling is, have you considered the lead-in frost effect?
That is actually in the back of our heads as you're going through it, and we are considering that, and we're trying to set it so that the outer wall temperature of the chamber is not actually going to be at a temperature where we would run into that.
Okay, because that could easily cause your critical failure, and that's just something. Those two things you really have to keep your eye on. I would hate to see a project this well thought out just end that quickly. So, apart from that, it's a lot of just really little things. But I will say this: I do like that you guys are paying attention to safety, and that you've worked with what's currently existing and the procedures that are remaining flexible for safety procedures, because that's always number one, is safety first. So, great job.
Thank you.
Yeah, not a whole lot here either. On slide 17, when you're doing the heat race, make sure you watch that those are subscripts, so it's not implying that it's Q prime times G or Q prime times W. On 23 is, I think, so you've got a third set, you've got 3 holes where the cooling flow is coming in. Is that correct? Okay, that's hard to tell from the top. You might also look at maybe staggering the offset from the inlet and outlet to try to make sure that you have the fluid mixing in there. 27. On the valve types, are those intending to be the types of valves, or are you just using that as general symbology?
In general, they are intending to be the types of valves.
Okay, so they're not all necessarily gate valves that you have indicated, you're just showing a general valve area.
Right. Okay. Which specifically the ones, relief valves are just relief valves, and we are using needle valves to represent the 2 throttle valves.
And then lastly, 47. That fuel throttle valve, that's manual, or you're actually in that?
So we'll actually, we'll be building support around that nozzle in order to turn with the servo.
Okay, it's great that you have the valve coefficient. Have you looked at what that would be for the range of flows that you would have and make sure that the operating range of that valve isn't where you're down, 5% closed or 95% open? Might just be something to look into.
Yeah, we're actually gonna have to get that particular valve and do some testing with it because they don't give you plots of the CV versus turns.
Okay. Yeah, you just don't want to find yourself where you're, like I said, one of those limits of the valve open or closed.
Okay, nice job. Are you measuring T in and T out of the cooling water? I saw on the GUI that there was at least one attempt I thought was labeled, but I didn't see the other. Are you planning on trying to track that or not?
Yeah, we are planning on tracking those
Okay.
temperatures.
Don't be surprised if you get big time lags on any of this stuff, especially if you're only running 5 seconds. You check your sensitivity of all your instruments in terms of how fast, what their response rate is, because this thing may lag miserably. How are you going to start this thing? Ignition was never mentioned.
Right, that's still a work in progress. Essentially, we're going to be working very simple, something essentially a stick covered in pyrotechnic compound stuck into the nozzle. We don't need to relight the engine, so there's no need to design, a spark gap injector or something that you would see more in industry. So essentially, it's just keeping it simple and keeping it inexpensive.
Okay, no problem. On chart 32, you've got your light doublet, and you've got you threw in the wrong picture. I'm sure you can get one or you can find one, but you need the little manifold. The fuel sprays against the fuel, not the opposite. So I think you just repeated.
Yeah, we do have that picture. I'm going to edit the slide. I changed out the wrong picture.
That's right, no problem. Overall, it's great. You guys, you've got plenty of things ahead. It'll be exciting. And time is your enemy.
Anybody else?
Okay. You said you wouldn't say anything.
So for the cooling jacket, have you done any thoughts on the pressure within that? How it affects the pressure requirements of your chamber wall, and then also the pressure requirements that you have over varying temperatures for the wall of the cooling jacket?
We're not really expecting to get pressures inside the cooling jacket that would really, on the scale of the 300 psi pressure on the inside of the engine, we're not really expecting to get anything that would come close to matching that scale on the outside.
Okay. I'll leave this last one. For the, so you're talking about using the fuel to cool the injector face, correct?
Correct.
When you designed the injector ports, did you account for that temperature change in the density of the propellant?
That is an interesting point. We will evaluate that. And again, the thermal analysis is still ongoing. We're still trying to tease the equations for that out of the spreadsheets. So once we do actually know how much heat we're going to expect in the fuel, we can run that again and make sure that our injector port sizes hold up.
Okay, cool. I'll give you the papers after.
Very nice presentation. You talk about the sizing of the components using RPA as your main driver for those. Did you guys do any hand calculations or any rough idea of confirming the values that the program put out?
Yeah, we checked some of the types of hand calcs. We went through and confirmed our nozzle throw and found that matched, and our nozzle expansion and then contraction ratio is the overall chamber diameter is a value we fed into RPA and chose ourselves. So.
Okay, very cool. And then for the pressure transducer you guys are planning to use to measure the chamber pressure, is that transducer located directly onto the chamber, or is there kind of some other system you're using for that? I'm worried about temperature.
It'll definitely be piped away for the temperature reasons.
Good job.